Okay, so we are going to continue on with organic chemistry, and in this, we are going to talk about specifically, we're going to spend more time on the alkanes. So, in our last notes, we talked about what an alkane, alkene, and an alkyne were, just very briefly, and we talked about tables P and Q. So, in your study of your notes today, make sure you have table P and table Q, right? You want to use those tables while you're using these notes. And this is going to be page number 36 in your notes book. Okay, so we have the alkane series, right? This is called the paraffin series. Do you need to know that that's the paraffin series? No, but you do need to know what an alkane series are. So the alkane series are carbon compounds where all the names end with ane. According to table Q, right? So table Q, right? They all end in ane. They're all carbon-carbon single bonds. So that makes them saturated. All right. So I like to remember this as single bonds start with S, saturated starts with S. So what does the word saturated mean to you? Well, when we talked about our solutions unit, saturated meant holding the most solute in a certain amount of water at a certain temperature, like being full. And if the air is saturated with humidity, it's full. So saturated basically means full. And so it means it's full of single bonds. And it means it's got the most possible number of hydrogens, right? And we have another homologous series going on, right? So we can go from 1 carbon up to 10 carbons. Actually, you can go beyond 10 carbons, but we're only going to focus on the first 10. And we're only going to go up to 10 carbons in any of the ones that we do. So our first is methane, because our prefix meth means 1 carbon. Do we agree? There's 1 carbon there. The word ane ending means that there's single bonds. So I have 4 single bonds for methane. So then we have a molecular formula. Remember from when we did formulas, molecular formula tells you exactly how many each element there are. So there's 1 carbon to 4 hydrogens, right? It's a 1 to 4 ratio. So now we have ethane. So now our prefix eth means 2. And then the ane means single bonds. So I have 2 carbons connected in a chain by single bonds. So there's our 2 carbons connected by a chain by single bonds. And at the end of all of those single bonds, right, outside of the 2 that are connected between the 2 carbons are always hydrogens, because these are hydrocarbons. So then we have our empirical formula, which is, where is it? So we have our molecular formula is C2H. So it's going to be, if you can't see it right now, it's C2H 1, 2, 3, 4, 5, 6, H6. And then we have our condensed structural formula, which is CH3CH3. So that means this is a structural formula, right? So I have all of those lines. The molecular formula is what we type on a typewriter. The condensed structural formula allows us to show structure, but still being able to type on a keyboard, but it's just squashed together. So CH3, right? So that goes to this. CH3 goes to that. So now this is what we call a ball and stick model. So this is what you would build in lab if we were in school right now. And then we have a space filling model. So don't worry too much about these. So these are the ball and stick and the space filling model. So this is how they are oriented in space. So remember how I said that it was a tetrahedral, right? So that's the 4-sided pyramid, right? Because you have this one side, and then in the back, right, you have the one side, 2, right? And then 3. And then where's the 4th one, right, is on the bottom. All right, so hydrocarbons are used as fuels, right? Propane. And here's our structure for propane, right? CH3, CH2, CH3. So here's our structure for propane. So count the carbons, 1, 2, 3. That's where we get the prefix prop, ane, connected by single bonds. And then it's C3H8. So if I were to look at table Q, the alkane series is going to be, hold on, I'll just scribble that out there. Okay, so table Q, it's going to match our formula. So here's our two structures. We've got propane and butane, right? So these are fuels. And this is bute because it's 1, 2, 3, 4 carbons. ANE because it's connected by single bonds. So then when you take this condensed structural formula, CH3, that's with this part here, then I have a CH2, CH2, CH3. That's the condensed structural formula. Now here we have our molecular formulas. C3H8, C4H10. These match the CNH 2N plus 2. So that's for an alkane, where N is equal to the number of carbons. So if I have 3 carbons, 3 times 2 is 6, plus 2 is 8. If I have 4 carbons, 4 times 2 is 8, plus 2 is 10. So that's how you use the general formula from table Q. And remember, these have single bonds, so they are saturated, right? SS, single bonds, saturated. Look at how full of hydrogens they are. So we have this general formula, CnH2n plus 2, right? So we have our name, octane. So what does that tell you? It tells me that there is 8 carbons connected by single bonds. Nonane tells me there are 9 carbons connected by single bonds. So here's octane, condensed structural formula, molecular formula. So does this match? So if I have 8 times 2 is 16, plus 2 is 18. Yes. So it matches my general formula for the alkanes. Now let's take a look at nonane. Right? Here's our condensed formula, right? So CH3, CH2, 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 and CH3. Okay, so we have that condensed structural formula. Notice single bonds, you're going to have CH2s in the middle, and then you have CH3s at the end. That's how another way I'm going to know that I have an alkane. So I know I have an alkane based on how my condensed formula looks and how the molecular formula matches the one that we have on table Q. Right, so C9H20 matches 2N plus 2, right? Because 9 times 2 is 18 plus 2 is 20. So what kind of intermolecular forces are there between nonpolar alkane molecules, right? Those are those van der Waals forces, right? Those are those very weak intermolecular forces. So the bigger, the longer the structure, the stronger the van der Waals forces will be. Remember, boiling point, melting point, and phase all have to do with the kind of intermolecular forces there exist between molecules. If you have a high melting point and a high boiling point, that means you have stronger intermolecular forces. Low melting point, lower boiling point, right? Those are going to have weaker intermolecular forces. So which one is a saturated hydrocarbon? So saturated means single bonds. And so which one is going to end in single bonds? I'm going to look at the endings, right? These are all have F, so I can't even use the F. So it's either YNE, ENE, OL, or ANE. And that's going to be our ANE, ethane. So when we have our methane, ethane, butane, propane, octane, right? Octane is going to have a higher boiling point and melting point than methane. This is why methane exists as a gas. And octane, where you might have heard that before, is with gasoline, right? Because gasoline usually has an octane rating. The main component of gasoline is octane. So there's going to be a much stronger intermolecular forces, the larger number of carbons. Okay, so let's draw the structural formula for butane. So the prefix but, according to table P, means 4 carbons. ANE means that I have single bonds connected them. So I'm just going to draw over here up at the top. So I have 1 2, 3, 4 carbons connected by single bonds. Now, the last thing I need to do is I need to make sure that every carbon always has to have 4 bonds around it because it needs to have a stable electron configuration. This first carbon only has 1 bond, right? It only has 2 shared pairs of electrons. So it needs 1, 2, 3 more. And those are going to be where my hydrogens go in the hydrocarbon. So now this second carbon has 2 bonds. It needs 2 more. So then hydrogens go there. And this next carbon, the third carbon, has 2 bonds. So it needs 2 more bonds with hydrogens. And then this last carbon needs 3 bonds with my hydrogens. Okay, so 62 done. So at standard temperature, at standard pressure in 298 Kelvin, which alkane is a liquid? So what I need to do in this case is notice how all of those boiling points, this is a short answer from a Regents exam. So these are all in degrees Celsius. So I need to figure out at 298 Kelvin which one's a liquid. So that means which one would have melted or has not yet boiled. So let's convert these to Kelvin. So if I have Celsius and I need to go to Kelvin, so Kelvin is equal to degrees Celsius plus 273. So if I have a negative 162 and I add 273, so this is going to be, hold on, that's 111 Kelvin. So at 298, if it boils at 111, this is going to be a gas, right? Because it boils at 111. So at 298, it's definitely boiled. So we have 89 plus 273. So this is 184 Kelvin. So 298, right? That's way above the boiling point of ethane. So this will also be a gas because it's boiled. So propane is negative 42 Celsius plus 273. So this is going to be 231, which again, this is 298 is above. So propane will be a gas. So then if I have 0.5 plus 273, so this is 272.5. So again, this is 298. The temperature is above the boiling point of butane. So butane will also be a gas. So then pentane is my only other choice. So, but 36 plus 273, let's prove it. This is 309. So it has not boiled at 298. So that means it's going to be a liquid. And what is the boiling point of propane in Kelvin? Well, we already did that. That's 231. Okay, so here we go, and there we go. So that wraps up this part